we've got x equals 19 over 9 here. Do I have any agreement at all? Yeah, I'm getting some nods in the head, which is great. One quick way, of course, that we can check this, being that there's no working, is that we can just take that value for x and substitute it back in. Let's just quickly do that right now. The left-hand side, if I put this everywhere I see x, will give me this. When you multiply a fraction by 3, rather than doing the numerator, the first thing you should check is, can I cancel anything? Like, will that make things a bit easier? And I can, right? If I cancel this 3 with one of the 3's in the denominator, what do I get left with? Once it cancels, right? That 3's gone, it leaves one of the 3's down here, right? 19 over 3, take away 1. A fraction, take away something else. What is your instinct to do with that? 19 over 3, take away 1. How many thirds are there in 1? How many thirds are there? There are 3 thirds, right? So therefore, I could write this as 19 over 3, take away 3 over 3. I know how many thirds that's going to be, 16 thirds. Is that 16 thirds?
Yeah.
Checks out. So good job, all looks good. Here's Leo's working, you can see where he's gone down. He's more or less, in fact, I'm pretty sure every single step he's done, he could have done had this been an equation, not an inequality, right? Do you see what he's subtracted 2x from both sides, he's added 1 to both sides, he's simplified here. What's he done on the very last line of working from here to here? He's divided by 2. Everything looks good. It is an inequality, so what might have been different? For example, if this last line here was not 2x but minus 2x, what would have gone differently on the last line? Yeah, Agni. Yeah, very good, because we know that an inequality can be true, but if you multiply and divide by a negative number, the inequality is no longer facing in the same direction. It flips around, okay? But luckily for you, everything was hunky-dory, so just like an equation. And what do you think of his number line? You look okay with that? Yeah, he's got the most important point. He's got the boundary. This circle here is hollow. Why is that? Okay, you don't include the 4. It has to be bigger than it. So all looks good. Does anyone, I mean, you didn't come up to the answer, but I'll put you on the spot now. Did anyone get an answer for 3? Anyone? Yeah, Kushi.
128.
Okay, let me leave a bit of space. X is 128. To get to x equals 128, the tip was rewrite this as an exponential. It's a log equation right now. So if you can't remember how to do this, let me remind you. Exponentials and logs, both of them have a base. See this one? It's the lowest number here. It's a 2. The base in both is the same. So on the next line, I'm going to have 2 as the base, not of a log, but of an exponential. These two numbers here are just going to swap places. So 2 to the 7 will be x. You see how they've kind of done a bit of a switch there? Like so. So the base stays the base and everything else switches. 2 to the 7 is 128. So there you go. Okay, any questions? Happy times? Would you rule that off? And then the heading I'd like you to make is variation. Variation. Now, we're starting a cool new topic today, and this topic is going to have lots of drawings in it. Now, I don't know how you feel about drawings. A lot of people aren't keen about drawings because they take a long time to do well. But I really like drawings because you guys have you heard the phrase, a picture tells 1,000 words? Have you heard that phrase before? Right? Very old phrase. The whole idea is, if you could draw a good picture, it conveys a lot of visual information very quickly, which if you had to read it out in like a paragraph or something would take you ages, right? So we're going to be drawing some pictures today, and they're going to be based on this idea of variation. So let me tell you what this means. Variation, ... is when you have two quantities that, now, in maths, we're interested in numbers that change, right? This is why we introduced algebra, because very frequently we're not just interested in numbers that are equal to something particular, but numbers that can take on a range of different values. So when you've got two quantities that change, but they change in relationship to one another. Let me say that again. There's two quantities, bless you, that change in relationship to each other. And there's two ways that this can happen. Firstly, when one thing gets bigger, when one quantity gets bigger, the other one might get bigger along with it. So as an example, excuse me, the more money I've got, the more donuts I can buy. There's two quantities, okay? The amount of cash in my wallet and how sick I'm going to feel after I finish my dessert, okay? More money can buy more donuts, okay? So here are two quantities, and you see they change in relationship to each other. They both increase at the same time, okay? So if both increase together, then we call this direct variation. They vary directly in relation to each other. Another word you might hear instead of variation, and I think the textbook's title for this is proportion. We would say that these things are proportional to each other. The number of donuts I can buy is proportional to the amount of money that I have. So this is a pretty straightforward idea to get across. But there are some quantities, you pair them up, and in fact, as one increases, the other one decreases. Let me say that again. Rather than both increasing together, sometimes a pair of quantities will increase in one and decrease in the other. So one's increase, oops, doesn't need an S on the end, leads to the other's decrease. Okay. Example. The number of donuts that I'm going to eat versus the number of people I'm going to share it with. Okay? Does that make sense? I'm like, oh, I walk in with this box of donuts. I'm suddenly going to share it with 31 people rather than one person. Then the amount of donut I'm going to eat is going to be smaller. One thing increased, the number of people who are sharing. Therefore, the other thing decreased the amount that I was going to eat, or the amount that each individual is going to eat. Right? We don't call this direct variation. We call this indirect or inverse variation. Or just like before, you might see this word proportional. So you might see it called inversely proportional. That should say directly proportional. Sorry. Okay, so you might like to just put the example, maybe you want to do a crude drawing here. Dollars and donuts. And then this is, that looks like $0, but anyway, I'm not very good at drawing donuts. Does that look more donut-like? Yeah, it looks like a donut, right? There we go. Okay, and down here, this one where one increases and the other decreases, I suppose I would put people and donuts again. Okay, visual arts, never my strength. But you get the idea, okay? More money equals more donuts for me to eat, but more people means less donut for me to eat. That's sad, isn't it?